to go into the theory of eccentric loading of columns. Now, what do we mean by eccentric column? What do we mean by eccentric loading? Okay, so as you can see, based on this figure over here, this is our centroid. Okay, so this is our centroid. And I want you to observe the load P is not loaded in line, right, with the centroid, and it has an offset distance. Which is E for this case. Okay, so with that in mind, we know at point A, because of the offset, okay, so what you see over here, this is the load. Okay, this is the loading situation. Okay, loading situation or configuration. Okay, so even before buckling, this is before buckling. Okay, even before buckling has occurred, we have a load, we have X load applied in P. What we did is we shift the load to the centroid, as you can see over here, right? And we have a moment M multiplied by E, because the moment, the force is on the left-hand side of the centroid, so it's inducing a anti-clockwise rotation. Okay, so in eccentric loading, what we have is also buckling, as you can see over here, and this is how the structure will buckle, and Y max is exactly at half the length, or L/2. Okay, so Y max occur at X is equal to L/2. Okay, now, so I have to draw our transformation. This is our Y, and then this is our X. So now, if we pick a point Q over here, okay, and I were to draw the free body diagram, which I've done over here. Okay, so this is at point Q. Okay, at point Q. At point Q. Okay, so moment at Q now. Okay, moment at point Q is equal to, so you have a PE, and this is our counter moment. PE will have a counter moment. So the counter moment is going clockwise, so minus PE. Right. However, we have another moment, and the next moment is generated by P multiplied by a perpendicular distance Y. So if we put our point over here, we are going to have another rotation in a counterclockwise direction, and this is P multiplied by Y. So we have to have a counter, which is, so this one is minus, so minus EY. So now our moment is different already, where P multiplied by E due to the offset of the centroid, and add P multiplied by Y depending on the position of Q where Y is. Okay, so we are going to address this as our equation number 1. Like what we have done before, we are going to apply the elastic curve theory. We're going to apply the elastic curve theory. So we know that moment is equal to EI d squared Y over dx squared, and then the whole thing will be equal to minus PE minus PY. Okay, and this I will address this as our equation number 2. So therefore, d squared Y over dx squared is equal to minus PE over EI minus PY over EI. Okay, so now we are going to let p squared, small p squared. Okay, small p squared is equal to p over ei, like before. Okay, when we were deriving for centric loading. Okay, so we know that this will be equal to d squared y over dx squared, and this will be equal to minus e squared minus p squared e, and then we have minus p squared y. Okay, then I'll bring the term across, so d squared y over dx squared plus by p squared y, this is equal to minus p squared e. Okay, and I will address this as my equation number 3. So we know that this will come out. I'm not going to go through how to solve a second order differential equation. Okay, but this is different. This is different. Why? Because now equation number 3 is not a homogeneous equation. Y is not equal to homogeneous equation because this is not equal to 0 if you have minus p squared e. Okay, so we know that it's going to have complex conjugate roots. So the general solution, okay, the general solution for complex conjugate roots are, okay, so what are they? So y as a function of x, so this will be equal to a sine px plus by b cos px, and now we have minus e. Why we have to have minus e? Because this, as I mentioned, is not a homogeneous equation. Okay, so this will become our equation number 4. So now we're going to put in our boundary condition, like what we see over here. Our boundary condition during deformation, what we have over here is we have when x is equal to 0, right? Y is also equal to 0. So this is our boundary condition number 1. And our boundary condition number 2, when x is equal to L, y is equal to 0. Okay, so we're going to substitute x is equal to 0 and y is equal to 0 into equation number 4, right? So we know that this is 0, and this will be a sine of 0 is also equal to 0. Cos of 0 is 1, okay? And then this is minus e. So we have the relationship b is equal to e, okay? So from here, y as a function of x will become a sine px plus by e cos px. Okay, and then we have minus e. So this is our equation for A. The next one, we're going to substitute our boundary condition when x is equal to L. Here we're going to substitute when x is equal to L, y is also equal to 0, and we're going to substitute into equation for A now. Okay, so I'm going to move for A. Right, so this will be equal to 0, and then we have a sine EL plus by e cos PL, and then we have the whole thing minus e. Okay. So if I were to move things around, I will have A sine PL is equal to E minus E cos PL. And then if I were to correct this out, you have E bracket 1 minus cos PL. Okay. Okay. And this will be our equation number 5. Okay. So we have to do something to this relationship. Okay. And we are going to do some side work. Okay. To determine. So what we're trying to do now is we want to determine the constant A. Okay. And it's not just so straightforward. Why not we just divide uh, E over sine PL. Okay, it's not just so straightforward. I want you all to see a form that has been used to derive what is the constant A equal to. Okay, so let's note, if we were to remember our double angles. Okay, so note, based on double angles, we know that sine 2 theta is equal to 2 sine theta cos theta. Okay, so now we're going to let 2 theta, which is equal to PL, and then we know that theta is equal to PL over 2. Okay, so if we were to let this so this is our equation number 6. Okay, so therefore sine 2 theta will be equal to sine, right, PL, and it will be equal to 2 sine PL over 2 cos PL over 2. Okay, so this is our equation number 7. Okay, so the next thing that I want to invoke is we want to know, we also know that cos 2 theta, note, again, based on double angles, that cos 2 theta is equal to 1 minus 2 sine squared theta. Okay, so with this, we can write cos PL, because 2 theta is equal to PL, is equal to 1 minus 2 sine squared PL over 2. Okay, so from here, right? So from here, we can I will rearrange this equation is basically 2 sine squared PL, okay, PL over 2 is equal to 1 minus cos PL. Okay, and this is our equation number 8. So what we are trying to establish down here is we are going to substitute equation 7 and 8, right, into equation number 5. Okay, into okay, so equation number 5 over here is this equation over here. Okay, is this equation over here. So A sine PL, okay, so we know we have A sine PL. So A sine PL is equal to 2a, right? Let me write down the form first. So equation 5, which is equal to a sine PL. And this is equal to E bracket 1 minus cos PL. Okay, and you can see how this is equation number 5. Okay, so A sine PL, right? We know the relationship of A sine PL over here. And A sine PL, right, is equal to 2 sine PL over 2 cos PL over 2. So on that front, we can write that this is equal to 2A sine PL over 2 cos PL over 2. And then the whole term is equal to, so this is equal to, so we know that 1 minus cos